We went to 1 or 2, but both programming with the D.
Wait. So let's get started. Okay. So for the map, Jason's Kumar listening for a couple days here. Jason's a good friend of well, actually, so your lineage is Stanford. Got a PhD at Stanford. He was a string theorist way back in the day, right? 1990s, when people cared. And then
I'll allow you that.
You'll allow me that.
I can't really disagree with that.
Okay.
Then we corrupted him.
Then actually he was officially corrupted here. So you went to.
No, it's officially corrupted at Michigan.
You went to Michigan. You were partially corrupted. Then you were fully corrupted.
Fully baked.
Fully.
Yeah.
So you came here to work with Oregon, and then you worked with Astronomy, a bunch of other people, right? So then San Diego, you had a postdoc.
That was before. So San Diego, Michigan, A&M, Irvine.
I know the institutions, but I don't have the right order. And then definitely the last one is Irvine, because that's where we overlapped as postdocs. And I was in the cosmology group, and he was in the phenomenology group, working with Jonathan Fang and Mark and Ron and those guys. And then he got a faculty position at 2008 to go to University of Hawaii. And he's been there ever since, and he works on lots of stuff. More recently, dark matter phenomenology and searches for low mass WIMPs through different methods, such as neutrinos, and that's something he's going to talk to us today about. So we had to talk about DUNE next week here, so looking at the theoretical applications of DUNE. Okay.
And so, thank you very much. And so I'm going to talk about directional searches at DUNE for sub-GeV monoenergetic neutrinos arising from dark matter annihilation of the sun. And so this is based on some work done with these collaborators here. In particular, a lot of the sort of introductory work was kind of done in this paper from last year, but the more recent work kind of focusing on directionality is from this paper from last month. And so one of the ways we can search for dark matter is by looking for dark matter annihilating in the core of the sun. And the idea is that when dark matter scatters off solar nuclei, then it can get gravitationally captured and eventually collects in the core of the sun. And the rate at which it's captured is determined by its mass and its scattered cross-section with the nuclei in the sun. And so then, that dark matter, as the density increases, it annihilates the standard model particles. And if you're in equilibrium, then the rate at which it's captured is related to the rate at which it annihilates. And what you're basically looking for are the neutrinos coming out of these annihilation products, because that's what's going to get out of the sun and get your detector on them. And typically the focus is on looking for a smooth distribution of high energy neutrino events above your background. But I'm going to focus on a different possibility, which kind of comes in sort of 3 different parts, which is, on the one hand, looking for models in which dark matter annihilation can actually produce monoenergetic sub-GeV neutrinos, looking for detectors and strategies which can resolve this kind of a line signal. And then the more recent focus is on trying to obtain directionality information from the neutrinos, in particular, seeing if this neutrino is actually coming from the direction of the sun. And I'll try to argue that DUNE becomes a really nice place to look for this type of search. And so kind of the standard lore for how we look for neutrinos coming from dark matter annihilation is that the first thing that you should expect to get a continuum signal, so some continuum of neutrinos. Basically because in most of the models you consider, dark matter is going to annihilate to some heavy particles, and then when those particles decay, you get some cascade, and that's where you get some continuum neutrino spectrum. And what you want to look for are the high energy neutrinos coming out of this process. For a couple of reasons. One is that they're going to have essentially a larger scattering cross-section with the nucleus in your detector. And so essentially your detector is going to have a larger effective area for those high energy neutrinos. And you're also going to face a smaller background coming from atmospheric neutrinos. And what you want to do is you want to try to use directionality, but really for high energy neutrinos again. And so the idea is that you want to cut down your background by trying to identify neutrinos which are coming from the direction of the sun. And the way you do that is, at all these neutrino detectors, what you're really looking for is the charged lepton produced by this neutrino from a charged current interaction. And so you want to rely on the fact that if it's a high energy neutrino, then your center of mass stream is boosted, and everything's going to be boosted. Your charged lepton is going to come out, in a very forward direction. And that's really going to be true, but really only if your energy is significantly above a GeV or so. Otherwise, for lower energies, basically your charged lepton is going to be roughly isotropic. You don't get much directionality from that. But kind of the points we wanted to make are, on a theoretical side, in the absence of minimal flavor violation, or if your dark matter is not a Majorana particle, then you can easily end up getting dark matter annihilation to light thermal. And in particular, we want to focus on a case where you annihilate to light quarks, like up, down, or strange. And what happens there is that as they shower and hadronize, you can end up getting things like K+, for example. And then when those sort of are produced with some high energy, they interact with the solar medium, and they slow down their hadronic cascades. You produce a bunch more, and you end up with a lot of stopped hadrons, basically stopped K+, which are decaying at rest. And when that decays at rest, you end up getting a 236 MeV monoenergetic neutrino. And that's the thing you want to try to look for. On the experimental side, DUNE can end up doing pretty, very well at the total energy reconstruction for a charge current interaction like this. So that can be sensitive to this kind of a line signal. And you can also get directionality on the neutrino. Again, not from the lepton direction, because that's going to be roughly isotropic, but from the direction of the nucleon recoil. And that's something DUNE can be sensitive to.
Sorry, a question. So how precise is the stop kaon argument? How well? You're assuming that kaons are essentially decaying at rest.
Yeah.
So how good an approximation is that?
It's a good approximation. In fact, this is kind of the standard lore, but we also simulated it in JON, as we'll see, and that's what you end up finding. Yeah. And so this will end up being great for reducing systematic uncertainties, and it's really a new kind of directionality search. I think it's the first time people have tried to use the nucleon as opposed to the lepton for this kind of a directionality search. And so, I'm sure a lot of you have heard this before, but let me just kind of review again the idea of how we search, for dark matter annihilation in the sun using neutrinos. And the basic idea is that as dark matter is passing through the solar system, if you interact with the solar nucleus, then you lose some energy to the elastic recoil of the nucleus. And so the dark matter loses some kinetic energy. If it falls below the escape velocity, it gets gravitationally captured, and it just starts orbiting and orbiting, interacts more and more, and eventually it collects in the core of the sun. And so then the dark matter is just going to annihilate the standard model matter. And what you're looking for are the neutrinos. That's what's going to get out. So by measuring your neutrino event rate, you get a constraint on the annihilation rate for dark matter. But for the region of parameter space we're interested in, basically the sun is going to be in equilibrium. So what comes out is the same as what goes in. So the capture rate is just equal to twice the annihilation rate. So your neutrino flux is actually then measuring your capture rate. But the rate at which dark matter is captured is just determined by the dark matter mass and by the scattering cross-section. And I just have a plot here from a paper from Andrew Zentner a while back. There are a bunch of different versions of this, but basically the idea is that given the mass and the scattering cross-section off your nuclei, you can figure out the rate at which dark matter is captured. And we're going to focus on the case where the scattering is spin-dependent, just because for spin-independent scattering, the bounds from direct detection are already so strong that you're not going to really gain anything by using neutrino detectors. But for spin-dependent, scattering off the hydrogen in the sun can actually give you bounds which are competitive or even can surpass what you can get from direct detection. Now, usually in this kind of analysis, you ignore dark matter annihilation to final state quarks. You try, or to light final state quarks. You look for dark matter annihilation from sort of harder channels. And there are a couple of reasons for that. One are sort of theory assumptions on what kind of dark matter annihilation models we expect. And another is the fact that these light hadrons, when they decay, are going to end up producing, or going to decay at rest, are going to produce soft neutrinos. But I'm going to kind of want to go through these sort of one at a time and see what are the ways we can get around these kind of issues. And so first on the theory side, we can say, why not look at, say, dark matter annihilating to QQ bar, where those are, say, light quarks. And usually the reason why we don't think about that is something we can just understand from angular momentum. And so the idea is that if our initial state is, Majorana fermions, as dark matter annihilating, then you essentially have two identical fermions annihilating. So your initial state wave function has to be totally antisymmetric. So that means you're either in an L equals 0, S equals 0 state, or L equals 1, S equals 1. And I'll ignore the higher L's just because those will be even more heavily suppressed. Now your outgoing fermion and anti-fermion pair are going back to back. And we just want to look at the angular momentum projected along that direction of motion. So I'll just call that the z-axis. And so LZ is going to be 0, just because if your particles are going back to back on the z-axis, then your wave function has to be non-vanishing that data goes to 0. And so just expanded spherical harmonics, that's only going to be true when m is equal to 0. So your spin projection and your total angular momentum projection of the final state are going to be the same. So if you started off with this initial state, that's a j equals 0 state. So j is equal 0, SC is going to be equal to 0. You really only have 3 possibilities, 0 or plus or minus 1. So you're going to be in that SC equals 0 state, in your final state. So your fermion and antifermion have the opposite spin. They're going back to back, so they have the same helicity. That means they're not CP conjugate to each other, so they're coming from different vial spinners. So something in your matrix element, your annihilation matrix element, has to be mixing those two vial spinners. But if you assume minimal flavor violation, then anything which mixes those vial spinners has to be proportional to the mass of that fermion. So you're going to get a suppression in your matrix element, which goes like the mass of the quark. Since these are the like quarks, that suppresses that part of the matrix element. On the other hand, you might have been in this initial state. In that case, this could be a j equals 1 state, in which case jz could be plus or minus 1. So in that case, both particles are spinning in the same direction. They're going back to back. So they have opposite velocities. They're from the same vial spinner. So you don't need any vial spinner mixing. You don't get any mass suppression. But you had to start from an L equals 1 state. So that means it's p wave suppressed. It's in the non-relativistic limit, and your dark matter is going to be non-relativistic. That annihilation matrix element is going to be suppressed. So either way, you get killed. And that's kind of the argument which underlies the theoretical prejudice toward looking for dark matter annihilation to heavier channels, like heavy leptons like BB bar, or tau tau bar, or to bosons like W plus, W minus. But the chirality suppression argument really relied on two assumptions. I assumed it was Majorana fermion dark matter, and I assumed I had minimal figure violation. And that's certainly true in sort of the standard ideas like the CMSSM, for example. But it doesn't have to be true in general. So for example, WIMPs just don't have to be Majorana fermions at all. And minimal flavor violation can fail even in the general MSSM. So if I don't make sort of the assumptions which take me down from the MSSM to a constrained version like the CMSSM, then I don't have to have minimal flavor violation either. And so for example, if your dark matter is a Dirac fermion, then your initial state could be an L equals 0, S equals 1, J equals 1 state. And in that case, you have no suppressions at all. It's an S-wave state, so there's no velocity suppression. Since it's a J equals 1 state, I didn't have to have any helicity mixing, so I can annihilate to light quarks. There's no suppression at all. On the other hand, even if your dark matter is a Majorana fermion, and I have to have some kind of a mixing of these vial spinners, if I drop minimal flavor violation, then the mixing doesn't have to scale like the mass of the quark. So the mixing can be large, there's no problem. So in either of these cases, we see that this dark matter annihilation cross-section to light quarks could have an order 1 branching fraction. So it becomes worth considering those channels when looking for dark matter annihilation in the sun. But then that kind of leads us to the second problem of why it's hard to look for neutrinos coming from that channel, even if that channel has a large annihilation rate. And it's basically because if you're annihilating some quark-antiquark pair in the sun, you're going to shower and hadronize and produce some set of hadrons. And what we're really going to care about are things like pions and kaons. But these things can be relatively long-lived. They're going to end up interacting through things like pion exchange with the dense solar medium. And they're going to stop in the sun before they decay. So since they're decaying at rest, the neutrino spectrum you get is going to be very soft. And usually you say, well, if it's a soft neutrino spectrum, I don't care. Because, first of all, there's a large background which you're now facing. But also the detector effective area becomes very small because for low energy neutrinos, there's a very small scattering cross-section with the nuclei in your detector. So usually you don't worry about this channel. But what a group of people in 2 independent papers pointed out in 2012 is that actually in that stopping process, all these, you essentially produce a hadronic cascade. So you can get a large number of pions and kaons. So essentially you can get a bunch of those decaying at rest. And so you can try to trade a hard spectrum for a softer one, but with a larger magnitude, a larger flux. And that can help you see this above background. And so actually, Karsten Roth, who's one of our collaborators on this sort of follow-up work, was on one of these original papers looking at this idea. And so as I mentioned, the thing you really care about are looking at pi plus and k plus decays. Really because, for example, you'll get pi knots, of course, also. But when those decays, you're largely going to get 2 photons, so you're not going to get any neutrinos out of that. So in the same way, you'll have pi minus, but that's going to end up being Coulomb captured by nuclei. So again, you're not going to get many neutrinos out of it. So the main decay which you're interested in is when pi plus and k plus goes to a mu neutrino and a mu plus. And so, since it's a 2-body final state, your neutrino is going to be monoenergetic. In the case of a pi plus, it's going to be about a 30 MeV neutrino with about almost 100% branching fraction. For a k plus decay, it's closer to 236 MeV with about a 64% branching fraction. So this is really like a monoenergetic neutrino, essentially a line signal. Now, of course, when the mu plus decays, you'll also get a neutrino and an anti-neutrino. And this earlier work from 2012 kind of focused on looking at that anti-neutrino, because there at a Water-Cherenkov detector, you can get inverse beta decay scattering off the proton, and that gives you a large cross-section. But the problem is that that's a continuum, so you don't get the advantage of this being sort of a monoenergetic signal.
Your neutrino, the flux, I didn't see the flux number. Is it expected to be above the atmospheric neutrino background or not?
Yeah. That's going to be the point of it.
Did you ever show that plot, how much bigger it is?
Yeah, I'm not sure if I have a plot, but I'll have a number for it. Yeah.
I'm sorry, I came a little late. Why do we even need the sun for this? So this is new dark matter annihilation.
Right. So the sun's going to give you a couple of advantages. One is that
it's an absorber basically.
Yeah, there are three. So one is that it's an absorber basically. So you're going to essentially just be collecting dark matter through gravitational scattering. So that's one reason you have a large concentration of it. Another is that it kind of kills a lot of the astrophysical uncertainties, because for a lot of these searches, like there's these searches in the galactic center, searches which are diffuse. On all of those, there's always sort of an uncertainty because your annihilation cross-section goes like the density squared. So even though you often get a good handle on the density, there can be local fluctuations in the density squared, which can change your annihilation rate a lot. But here in this case, you rely on the fact that the sun's in equilibrium. So it's capturing dark matter, the dark matter is collecting the core of the sun. If you wait long enough, what goes out is the same as what goes in. So you don't have to worry about what the annihilation cross-section is, what the density it is. You just know what got captured, and that tells you what came out. And the density itself is much more tightly constrained. So you kind of kill a lot of the astrophysical uncertainties. And the other thing is that you can now compare this to direct detection. So a lot of model things like Fermi or other searches where you look for dark matter annihilation, you either see something or you don't, but you don't know how to compare what you saw to, say, Lux or CDMS because they're looking at scattering, not annihilation. There's not a comparison. Here, because we're using capture, I can plot everything on the same plot, and I can, complement what Super CDMS or Lux will see with what these neutrino searches see.
But do you need to see the differences in spectrum? Because I know you also get just normal neutrinos from nuclear.
Yeah. So I mean, it comes through a couple of things. So because it's a monoenergetic signal, you can look at that. And you can also just look for, saying, if my background is atmospheric neutrinos, I have some estimate for what that should be, from cosmic ray data and from my calculations. So I should say I should see a certain atmospheric neutrino background. I can look for something above that. And the other advantage we're going to try to show here is directionality, because if it's coming from the sun, you can say that my atmospheric neutrino background is going to be largely isotropic. It won't be quite isotropic, but it'll be more isotropic than your signal just coming from the sun. So you can try to use that as well. And that's another reason why people like using the sun.
Just another comment I want to make is, if you're probably going to talk about 235, but you probably guessed that I would ask about 30 MeV, then it can maintain the coherence, then you get you can do the coherent scatter neutral current process instead of your charge current.
Okay.
And that would give you a factor of 10,000 boost.
Oh, okay. Right, okay, we should think about that.
And we don't lose coherence at 30 MeV, right? It's 50 MeV. You sort of drop it.
Yeah, your form factor is saving you a little bit by 30 MeV, but you have coherence.
All right, so then the idea is that in some sense you've now got most of the pieces, because given, say, your mass and your scattering cross-section with your nuclei in the sun, you know the rate at which dark matter is captured, so you know the annihilation rate. And you know that sort of, every stop K plus is going to give you one neutrino. So you just have to know how many stop mesons are you getting per annihilation to tell you what your neutrino flux should be in terms of your dark matter model parameters. And so we're just going to call that fraction R, which is essentially, in any dark matter annihilation process, what's the fraction of the center of mass energy, which is going into stop pions and stop kaons. And that's something we're just going to simulate, or which we did just simulate using Pythian kaon. So the idea is that the dark matter annihilation process, you just simulate using Pythian. Say dark matter with some mass annihilates to QQ bar, whichever annihilation channel you want. Pythia simulates your showering and hadronization. And the idea is to look at what are the long-lived hadrons which come out. What's that spectrum? You want to take that spectrum and just input that into JON and let JON simulate the interactions with the solar medium. And so then you get this plot of these various R factors. So essentially the fraction of the center of mass energy which has gone into pions or kaons. You can see that ends up decreases with I should say in particular to pi plus and k plus. And that decreases as you increase Mx. But you see that you're going to get about a factor of 10 more neutrinos per annihilation, at least for the up and down channels. These 30 MeV neutrinos coming from pi plus decay, compared to the 236 MeV neutrinos coming from K plus decay. So you're definitely getting more of these 30 MeV ones in the U and V channels. It's not quite as large an enhancement for the when you're producing strange cores. And so in our earlier work, we focused on both of these channels. But what I'm really going to focus on more for this talk is the K plus channel. And there are a couple of reasons. One is because Again, for a charge current interaction, again, not for coherent, but for a charge current interaction where you're getting an electron out of this, you're going to get a much larger cross section for a high energy neutrino scattering off your detector than for low energy neutrinos. And so essentially, the larger effective area of your target more than offsets the smaller number of neutrinos you produce per annihilation. Another thing is, in the end, we want to use directionality to reduce your background. And so because of that smaller effective area, for 30 MeV neutrinos, the number of events you're getting, both signal and background, is so small anyway that you don't really care about a directionality cut. There's no real payoff for it. You already don't have enough events. So really where it benefits from you is when you have these larger effective areas. And the other thing is that the higher energy gives you a better handle on directionality. Now, I guess, there's one more reason, which is that for a 236 MeV neutrino, of course, it's produced as a mu neutrino in the sun. But then you have to account for neutrino oscillations through the solar medium and then through vacuum all the way to the detector. And so it can emerge in any flavor. If it emerges at the detector as a mu or electron neutrino, then you can still get a charge current interaction producing a charged lepton at your detector, which you can tag on. For a 30 MeV neutrino, you're not going to produce a muon from that, so only the electron neutrino is going to work. And so where we want to look for this is going to be at DUNE, which is kind of really nice for this kind of search. So I have two possibilities for the setup for the far detector, which are just from their conceptual data report. And so the nice thing about it is that expect to have a large exposure, a good total energy resolution. And kind of important for directionality is that you think you can identify the outgoing particle tracks with good energy and with angular resolution. And so some estimates, I think current estimates for the fiducial volume is that it could be up to 40 kilotons, split into two different detectors. On identified tracks, you think the angular resolution could be up to 5 degrees or so. And our estimate for the total energy resolution is about maybe 10%. And so you kind of have all the pieces you need to do this kind of analysis. So you know what the neutrino flux is going to be from the sun arising from dark matter annihilation. Given the mass and the scattering cross-section, you can take that to the capture rate, that gives you the annihilation rate. With these R factors, you can turn that into the flux of monoenergetic neutrinos. We also have estimates for the background neutrino flux, which just come from this relatively old paper. Now, these numbers one shouldn't necessarily take entirely, with this level of precision, because these were computed at the location of super K. And so at DUNE, it's a different calculation. But the precision you'll end up getting if you just go ahead and do that for DUNE will be similar. The numbers might be different on the factor 2 level or so. But you're going to be able to get these numbers.
So you want an energy range that corresponds to?
This is at about 236 MeV.
At 236. Oh, that's pretty low. Okay, that's actually pretty uncertain. Okay, anyway.
Yeah.
I think there's
Yeah.
You're right. There's actually lots of schematics there.
Yeah. Right. But hopefully you'll be able to sort of try to do this actually for DUNE as opposed to doing this for CAMU. But
yeah.
Right. And so you'll also have to worry about the flux for antineutrinos, which is similar there, because unless there's some other tagging information, you'll also get two charge current events at 236 MeV coming from atmospheric antineutrinos. And the name of the game is just looking for a charge current interaction where your energy deposited is within your energy resolution of 236 MeV. So and there'll be ways to get around the antineutrino background, but in general you'll have to worry about that as well. So the last thing you need is just essentially the effective area of your detector for these signal and background neutrinos, which essentially amounts to just knowing that the charge current neutrino nucleus scattering cross section. So that is just incoming neutrino comes in, it's scattering off one of the neutrons, converts it to a proton, and you get a charged lepton coming out. And so for this energy range at 236 MeV, this is where it's in some sense most complicated theoretically, because you're not at a high enough energy like above GeV where it's deep and elastic scattering and you think you know that reasonably well. You're not at a low enough energy where the structure of the nucleus doesn't matter so much. That's relatively well understood. It's a charge current interaction in a region where you need to know the structure of the nucleus, and that's the part which is not understood very well. It's not only it should be quasi-elastic, but it's just not understood how to compute that well. And so people basically rely on numerical packages. In our earlier work, we ended up using Genie. We later ended up using Neuro. I'll kind of get to why we made that change a little bit later. But these are roughly the cross-sections you get for an electron or mu neutrino to have a charge current interaction. This is what we got from Neuro. And so we can kind of put these pieces together to look for the sensitivity of a non-directional search. So the idea is just They're looking for a charge current interaction where you produce a lepton and the total contained energies within an energy resolution of your 236 MeV, not trying to take any directionality into account. And if your energy resolution is about 10%, and you have an exposure, we just took as an exposure maybe 34 kiloton years, maybe what DUNE could get in a year or so. You just think the number of background events you would get is about 50. And so if the number of events you actually observe is consistent with that, you could say, what set of models could I exclude at 90% confidence? And that corresponds to this blue line around here. I'll state here that the effective areas that we computed using Gini, I think Neuro gives you numbers in a factor of 2-ish or so.
How do you estimate the background effects? What are the contributions?
Oh, just this energy is done only from atmospheric efficiency. Yeah. Now, there are some other lines here I'll just kind of go through. So this green line is if you try to do a similar type of thing using CAMLAN. It's a liquid simulation detector, but you'll also get good timing resolution, or good energy resolution. And you can identify lepton tracks. This is something they've been working on recently by looking at the timing of when the PMTs light up. You can reconstruct the track which originated your simulation light. So they've been working on that recently. But of course, this is going to be much worse just because you have a much smaller effective area for these 30 MeV neutrinos. Now, this dotted line is what DUNE can do looking at the pion channel. I'm sorry. CAMLAN, the smaller effective area is just because it's smaller. This dotted line is what DUNE can do looking at the pion channel. That also suffers from a smaller effective area, this time because you're looking for a charge current interaction with a 30 MeV neutrino. And this gray line here was the original work which Carson and company did, looking for not this monoenergetic neutrino, but looking for the continuum antineutrino through inverse beta decay. And there you get hurt just by the fact that it's not a line signal. Now, here are some lines from, this is an older Pico2L bound. I think since this paper, they've had a more recent one, which I'll show a little bit later, and Picasso. And so you can see in the 4 to 5 GeV range, you end up being competitive with direct detection, so only in this low mass range. And unfortunately, you have to cut off at about 4 GeV or so, just because when your mass gets too low, dark matter can start evaporating out of the sun. So even though you're in equilibrium, annihilation isn't the only way for dark matter to get out anymore, to get out through evaporation. So your bounds start getting weak again. But what you'll see here is that these two lines here are from Super K, with their current data, what they're capable of doing if they try to do like a low energy analysis of this for electron neutrinos, and what Hyper K could do with about 640 kiloton years of exposure. And so, those are always going to win with sensitivity, just because with water shrink-out detectors, you can always get a bigger exposure, and you can win that way. And there are no ice cube limits here or any of the other kind of neutrino searches, because they're usually focusing on these high-energy neutrinos. And what I've assumed was that spin-dependent scattering and annihilation entirely to the up or down channels. Those channels give you about the same spectrum. And in that case, you're not really getting any high-energy neutrinos, so they're not going to see any.
In terms of incoming neutrino energy, what's sort of the average threshold for DUNE?
I'm gonna get to that. So yeah, so maybe I can.
That's embedded into this figure somewhere, right?
Right. So we're essentially above that for all the stuff which is relevant here. So they have.
Okay.
Yeah. One way to look at it is that they have like a threshold for lepton detection.
Yeah.
Which their CDR puts that at about 30 MeV. So here, the idea is that So that's
probing some average.
Yeah, I'll get to eventually, but the idea is that for proton identification, it's like 50 MeV. For lepton identification, it's about 30 MeV. Well, if I don't care about the proton, I just want to see total energy collection, and I identify a lepton, and that's 30 MeV. Most of your energy goes into the lepton, and if it's 236 MeV coming in, you're pretty much going to be above that anyway. So for this purpose, we didn't actually worry about that efficiency. Later on, we're going to have to worry about more of the proton efficiency, but we'll plug all of it in.
Why is your sensitivity improving with lower and lower mass? Is it purely from number effect? How many WIMPs do you have? Yeah, number effect, and you're not being killed by anything. So for the other ones, for direct detection, of course, you're always killed by thresholds, right? Here, what really is killing you, your neutrino threshold is fine because they're all coming out with the same energy no matter what the mass is. The real thing which is killing you is when evaporation starts taking over. So that kind of makes it go really bad at 4 GeV. No, that I understand, but as you go to lower and lower WIMPs, your sensitivity is improving.
Yeah, it's all a number.
It's a number.
Yeah. Okay. So as we can see, even for just this 34 kiloton year exposure, in this 236 MeV neutrino channel, your background is starting to be significant. You're getting like order of 50 events or so. So it'd be nice to get a directionality cut, which is going to preferentially select the neutrinos that are coming from the direction of the sun. And so that's going to reduce your systematic uncertainties by looking sort of on axis in the direction of the sun versus off axis. And I kind of like to think of this as almost like a two-step kind of process. Because really what you'd like is for your signal to background ratio to be larger than your fractional uncertainty in your background rate due to systematic uncertainties. Because that tells you that if you see an excess which is growing with your luminosity, with your exposure, that it's really some kind of an excess and not just you underestimated your background event rate. And so one thing you can do with this is that you can get a measurement of your background event rate by just looking at events which are not pointing from the direction of the sun. So that kind of reduces the right-hand side of that, reduces your systematic uncertainty in your background rate. But then when you go on axis, you can increase your signal to background ratio because you're not cutting much of your signal, but you're cutting a lot of your background. So you kind of improve both sides of this inequality. And of course, the other thing is that if you reduce your background preferentially compared to your signal, then that can improve your statistical significance. And so most searches for neutrinos arising from dark matter annihilation in the sun try to use directionality for these reasons. But usually it's when you're looking for a very energetic neutrino, because again, the idea is that you're producing a charged lepton. You want a large energy so that the whole system is boosted away from the sun, so your charged lepton gets focused forward. And once you get to sub-GeV energies, you're essentially not boosting. Your center mass frame is not boosted very much. The lepton doesn't get much of a boost. It's coming out roughly isotropically. But the nice thing is you can use the hadronic recoil, which is always going to be forward pointing. And so for 236 MeV neutrinos, you can get a significant number of events where essentially your lepton comes in and converts a neutron to a proton, but the proton gets ejected out of the nucleus. So essentially I have events where your lepton is hitting a 40 argon nucleus, you produce, your neutrino is, you produce a charged lepton in some direction, a forward-directed proton, and a 39 argon nucleus. And so what you'd like to do with DUNE is to identify this track as well as that track, and to cut on the direction. So in this case, again, you need not only the cross-section, but you need the angular distribution as well. And all of these things, this is in a region where it's sort of maximally difficult to do any of that. And so we're going to rely on numerical techniques. In particular, for this part of this, we used a package called Neuro. And I'll get into a little bit of how we did that and why, how we use Neuro and why. And so the idea is to generate about 100,000 events for each of the neutrino flavors, electron or muon. And then try to tag on events with one identified charged lepton track and exactly one ejected proton, which is with an identified track. And I'll just note incidentally, that helps kill off your anti-neutrino background because anti-neutrino charge current interaction will tend to eject a neutron, not a proton. So that you should be able to identify. But I'll emphasize that the cuts are entirely at the event generation level. So there's no attempt to really model how the DUNE detector responds. You're really just generating events and then imposing threshold cuts on them, motivated by the DUNE CDR. So the lepton threshold is about 30 MeV. Again, that's not terribly constraining because typically the leptons are going to be much more energetic than that. The proton threshold, according to the DUNE CDR, is going to be about 50 MeV. So this is what we labeled as a tight cut. But just talking to people on DUNE, they say that that might be an overly conservative number. They might be able to do better than that. So some numbers which are thrown about is maybe they could do as well as 20 MeV. So we just decided to do another set of analyses, which are so-called loose cuts, where the proton cut is about 20 MeV. Now, in principle, if you could do that much better for the proton, you'd imagine you might be able to do better for the lepton as well. But we didn't worry about that since already, it's really the proton which is driving your efficiencies anyway. The lepton energies are above this in any case, so we just kind of kept this fixed here and varied the proton threshold between tight and loose cuts. And so the toughest part of modeling this kind of interaction is in understanding essentially the internuclear effects, intranuclear effects. And so the nice thing which Neuro lets you do is use a spectral function rather than a Fermi gas model for this. And that's part of the reason why the main reason why we switched to Neuro. And so I'll kind of describe a little bit what are the issues with these neutrino nucleus scattering cross sections at 100 MeV, and I'll preface it by saying this is completely a novice's view. This is not really what I focus on, but this is my understanding of really what are the issues not only some which Neuro solved, but some of the issues which are still outstanding.
Actually, sorry, what's the half-life of argon 39?
I don't remember, but you're saying can you use the decay of that to
Yeah.
also tag? I think you can, but we did not.
Okay.
We did not go through that analysis. So the basic idea for which is used is to use the so-called impulse approximation, which is basically you kind of break up your neutrino nucleus interaction into a two-step process. The neutrino interacts with the nucleon. The nucleon is struck, and then the nucleon interacts with the rest of the nucleus. And so it's to understand these subsequent interactions, you really need to understand the state of the nucleus. And so the simplest thing you can do is just model the Fermi gas. But sort of the more detailed thing you can try to do is to essentially use a spectral function, which is your estimate for what the wave function for the nuclear state really is, obtained from a combination of theory and then trying to match to some electron scattering experiments. And so this kind of provides a better model, and this is the thing which Neuro tries to implement, which I think is not implemented in GeNE. But the analysis is still based on the impulse approximation, that you can essentially factorize your scattering process into those two pieces. And that's estimated to be less valid, starts to break down for energies below about 400 MeV, which is right where we are. And so yeah, I'll kind of just refer to this paper here as a place which kind of describes some of these issues and kind of gives a set of references to these. In fact, I think these are the people who are involved in the Neuro project. But it kind of leads into a larger discussion of these kind of models. But kind of the real problem is that there's no real good tool for going beyond the impulse approximation. So everyone at this energy range just has to use it anyway. And so as I'll mention towards the end, in the end it'll be best just to try to calibrate, and there are ways to kind of calibrate your detector. So I'm really going to use this more as a proof of principle. And so then we can see, well, if we want to impose some kind of event selection directionality cuts, what are the kind of efficiencies? And there are really two factors which go into it. There's the event selection efficiency, which is just what's your efficiency for being able to identify a lepton above 30 MeV and a proton with kinetic energy above your threshold. And that's common to the signal or background events. It doesn't matter which direction they're coming from. And again, that's what we get from simulating in Neuro, and these are the efficiency factors we get for the electron and muon channels, either tight cuts or loose cuts. Now, then there's a directionality efficiency, which is what happens if we demand that we get events within a certain cone or cone half angle of the sun. And again, that is going to favor signal versus background, as you'd expect. So I kind of plotted it here as a function of the half angle. It's just geometric for the background. And here for signal events, I've coded it by electron is solid, mu is blue, loose cuts are black, tight cuts are red. You can see in all cases, you're really much better on signal versus background. And so that kind of drives the gain you can get from this kind of thing. And your total efficiency is just a product of these two. And the thing you care about is trying to either improve signal significance or your signal to background ratio. And what we chose to do is just to choose our angular cut based on trying to maximize signal significance for a fixed exposure. Now that's not the only choice you could have made. I'll actually show why you might want to make different choices later on. But just as a first run, this is the kind of thing we chose as our criterion for where to choose the angle cut. And so you can see, for any fixed exposure, if you have a certain signal to background ratio, you want to see how this changes when you impose these directionality cuts, or these selection cuts. You're just multiplying the ratio of the efficiencies for signal over background. For signal significance in the Gaussian limit, and that's what we're going to end up being, you're multiplying by that same ratio times square root of your background efficiency. And since this is always less than 1, you can see you're never going to do as well with signal significance as you do with signal to background ratio. But in the end, this is the quantity which we've chosen to try to maximize. And these are the cut angles which do it for the various, for either the electron or muon channel, or either tight or loose cuts. And so you can see that, first of all, these are all sort of well above this angular resolution of about 5%. So angular resolution is not really an issue for this. And I've kind of just written in this table here, what is the enhancement you get in the signal to background ratio, and what's the enhancement you get in signal sensitivity. So you can see, signal to background ratio can improve by, up to a factor of 5. And I don't have it on the table here, but that improvement of a factor of 5 over your non-directional search, what that amounts to is a signal to background ratio of up to a factor of 1.5.
Just to go back on side, it wasn't wrong. Your type cut has a higher efficiency.
The network connection.
Sorry, your tight cut has a higher efficiency than your loose cut.
No, the tight cut has a lower efficiency.
No, but on your curve, on your plot.
The directional cut, no, it makes sense, right? Because
So is it like your denominator is you've already chosen some sample?
yeah, well, things like a tight cut means it's a higher energy proton, so you expect it might be more forward
So
pointed.
for all the high energy protons, what is your efficiency of your signal for that? That's what you're.
Yeah, that's what the directionality is. So the directionality does not
It's
include
not the
selection.
signal efficiency.
Yeah, because I factored that out already. Yeah. Okay, yeah. So you can kind of see that, in fact, what you can see is that, you get a big enhancement with the signal and background ratio, but your signal significance really only sees a modest improvement. Basically, it's because you're killed by the selection efficiencies. Those efficiencies, you're just getting so many fewer events that it hurts your signal significance. In fact, you kind of see that the tight cuts tend to win a little bit more on signal to background ratio. The loose cuts are a little bit better for signal sensitivity. But, and so, we chose these cuts to maximize your improvement in signal sensitivity. Again, maybe since your big improvement is in sensitivity in signal to background ratio, that's the thing you want to more focus on. We just kind of made a choice to at least keep this comparable. But kind of the general lesson is you're definitely going to win more on systematic uncertainties than on statistical significance. And so, these are kind of the results we have. I guess, the direct detection lines, this is the more recent Pico 12 result. These bands are for the muon and electron channel going from tight to loose, where the looser bounds give you, or the looser cuts give you the more constraining dark matter bounds. And you can see we've done this now for 340 kiloton years exposure for a factor of 10 larger. And the reason, just because, again, your selection efficiencies are killing your event so much to really use this, you want to kind of just get a larger exposure anyway. And you see, again, the electron channel is going to win over the muon channel just basically because of the larger effective area, because your cross-sections are larger, you're not phase-space limited in your scattering cross-section. But again, you can see I still got the super K and hyper K lines here, and these are comparable, even for very reasonable exposures. Yeah. And so kind of the upshot of it is kind of what you expect, which is that just in terms of statistical significance, water electron detectors are always going to win, just because it's so much cheaper to build to get a larger exposure for that. But you really can't use directionality in this way to kind of reduce your systematic uncertainties, because you're really trying to look for a Cherenkov cone there, and since these protons are coming out, that's what's giving you your directionality, and they're non-relativistic. You're not going to get a Cherenkov cone from this. This is kind of a unique capability for a liquid argon TPC kind of detector like DUNE. We can identify the proton tracks very well. And so we're relying on numerical tools like Neuro, and that can be a dicey proposition for the reasons I kind of mentioned. It's really not well understood. But the nice thing is you can calibrate this with a stop kaon experiment. And roughly any stop pion experiment is going to be a stop kaon experiment too. The idea is that you take a proton beam, slam it at a large target, you produce a bunch of pions which stop, the pi plus stops decays, and you can use that to calibrate your detector. But if you produce pi plus, you're going to produce k plus as well. You've got to stop k plus experiment as well. And things like this are planned for DUNE. One example is the Daedalus experiment. So if these things go through, you're going to have a calibration for this. So I kind of, take some of the, the numbers from Neuro, these sensitivities, not so much as you can take this to the bank because we understand all of these things, but more that really this is just a proof of principle for what you can do. But in the end, when you have DUNE, you really want, to calibrate these kind of stop kaon experiments, or to use things like, the on-axis versus off-axis measurement to get a better handle on these things. So maybe I'll just conclude by saying that, dark matter annihilation in the sun can produce monoenergetic 236 MeV neutrinos. Basically, all you need is, either a model where your dark matter is not a Majorana fermion, or where you don't have minimal favor violation. In that case, there's no reason why you shouldn't annihilate, with a substantial branching fraction to light quarks. When they hadronize and shower, and those hadrons, interact with the solar medium, you get a bunch of stopped, K+, which will decay at rest and give you that low-energy monoenergetic neutrino. With a liquid argon TPC detector like DUNE, you can reconstruct both the energy and the direction of these products. And so not only is that very good for seeing a line signal, but by getting the directionality of the ejected proton, you can try to preferentially focus on neutrinos that are coming from the direction of the sun. And that helps you reduce your backgrounds and your systematic uncertainty. This kind of sub-GeV neutrino directionality is a unique capability for DUNE. And this kind of having any kind of a stop kaon experiment there would be a nice calibration for this kind of search. Thanks.
sub-GeV plot, not this one, but the earlier one. Yeah, so the thing that strikes me, I think we should talk after this, is like, so with the pions, top pion, you get 30 GeV, sorry, 30 MeV neutrino, then that's factor of 10 more flux, right?
Yeah.
So there's a factor of 10. And if you look at the neutral current, that's a factor of 10,000. So you're like 5 orders of magnitude more flux sensitivity.
Right.
Looking at lower energy neutrino than higher energy. So, like instead of a 40 kiloton, instead of that, you could do it at 40 kilograms.
Right. Yeah. Okay. Yeah. We had focused exclusively on charge current, but yeah, we should think about neutral current.
Of course, with the DUNE, your thresholds won't allow you, probably won't allow you to do that. There are other possibilities.
Yeah, but the directionality then is going to be difficult. I have a question too. So the way you compare with the direct detection experiments is basically the link is internalization in the sun or the same.
Yeah, assuming that you're in equilibrium.
So what I don't understand why, I mean, how does it affect your uncertainty and your link? Like for example, I assume that for larger mass waves or neutrinos, you have better thermalization on, let's say, nitrogen, or let's say on helium, you need to have much smaller because of just the kinematics.
Oh yeah. So
how does it affect your?
Yeah. So I don't have the figures here, but basically, there's thermalization time. Well, actually, I think equilibration time, which is a function of the mass of your dark matter, the scattering cross section, and the annihilation cross section. But usually for the things we've assumed, like for the mass ranges we're talking about here, because where it really only matters. I've plotted up to 100 GeV, but really, beyond 10 GeV, direct detection is winning anyway. For those masses, for the cross sections here, and assuming your annihilation cross section is close to a picobarn, so it can even be a couple of order of magnitude below, but not like 10 orders of magnitude below. If you're roughly in that region, then your equilibration time is less than the age of the universe, less than the age of the sun. So you say the sun should have equilibrated by now. Now again, I should caveat that by saying this is assuming, a relatively quiet, cosmological history for dark matter. If there was some stream which came through, some very local fluctuation, then you might not be in equilibrium. But this is kind of the standard assumption people use, and we're using too, which is basically if everything was relatively quiet, or you just look at your equilibration time, and there are no transient features, in the recent history, then.
So think like photolicity if sun doesn't affect you, since you are long.
No, not so much. Yeah.
All right, so Jason will be around the rest of the day. So if you have any questions, we'll get them before. So thank you again. WRO, I forget what it stands for, but it's some Warsaw